Now, Kalle, the stage is yours.
Thank you very much. Thank you. So my name is Kalle Åström, and I work in the math department at Lund University. And so many of my colleagues do pure math, but we are several researchers that try to do applied math and start to see how it works with other things. I work in a group, research that do computer vision. So we try to do algorithms that take vision as images or other data as input and try to analyze them in several different ways. And in this talk, I will describe two types of problems that we are interested in solving. So one is concerning semantics. That is concerning, if you're given images, can you write algorithms that interpret the images in terms of their content, that this is a chair or a human or a table, it's an indoor image, outdoor, or things like that. So these are like semantic structure. It could also be like we want to know what's happening in the image. Someone is running or jumping or talking to the phone or things like that. But these are concepts that are connected to sort of semantic structure, knowing what is actually happening in the image. And the other research area that we are working a lot with is trying to, also from image and other data, trying to reconstruct the 3D models of images. And I will give several examples on the first and second types of problems that we try to solve. Now many of these problems, they involve geometry, programming, statistics, but they also involve a topic called machine learning. And during the last couple of years, the topic of deep learning has become very important. But there will be several other speakers talking more about deep learning. So I will mention it, but I will not describe it too much in this speech. So basically this is it. Semantic and geometry, those are the two topics. And in the end, what is it that we want to do? We want to do both. We want to be able to write algorithms that can both do 3D structure for motion, but also semantics. And that's sort of the key of what we want to do. So basically there will be an introduction and then something about machine learning, very brief, but then these two topics, semantics and geometry, mapping and localization. So a little bit more about the department. The Department of Mathematical Sciences, we have three subjects, so mathematics, statistics, and numeric analysis. We're famous for world-class research in pure math, in the analysis of partial differential equations, for instance. So one of our previous professors, Lars Hermander, got the Fields Medal, and that's the best thing you can get in mathematics. But we have several other distinguished prize winners, and one is giving a talk later on today, Fredrik Kalle, who have been working a lot in the group, but now is working here at Chalmers. And within this research area, there are numerous research groups. Some are very small, and then some are fairly big. So we have pure math, algebra, analysis, or inference theory, and things like that. Within this group, we have a group that do computer vision. And computer vision, traditionally, it's a topic that perhaps is more likely to be in a computer science department or electrical engineering department. But in some places around the world, it's actually in math department. And computer vision needs all of these kind of tools, but it also needs a lot of mathematics. So it's a really good place to be in the math department to do that. And the research group that I'm working with have roughly 25 people. And we do research on these two topics that I'm going to talk about, geometry and semantics, or sometimes we call it cognitive vision. But we also do research on medical image analysis, but I will not be talking about that today. Also, in terms of being a math department, I think we are singular, at least in Sweden, but perhaps also singular in the world, in terms of that we are so interested in taking our algorithms and math and actually bringing them to startups. So here's a list of startups from researchers that have come from the math department. And it's growing, so there are a couple of more now. Some of these have been sold and are not active anymore as an independent company, and some are very much active still. Okay, so what's computer vision? Computer vision is sort of the art of going from pixels to meaning. So to the left here, we see a representation of an image. And each little box there is a pixel. It's a picture element. That's the abbreviation. And each box has a value. So it could be low value if it's dark, black, or it could be a high value if it's bright, if it's white. So basically, that is the representation that a computer has. And from that representation, we need to extract useful information. Now, if humans get an image represented like this, like a bunch of numbers, it's extremely hard for us to see what the image actually means. But if we get the image represented as a grayscale intensity changes, like we see here on the right, then immediately we can do things with the image. We can do calculations, we do things. We see that, it's a train, it's outside, it's a building, there are train tracks. So we have these amazing capabilities, computing power, starting from at the retina and going through the brain and doing all these kinds of things. And that's what we want to do in computer vision. We want to write those algorithms that can do the similar things. And doing that, in many cases, some parts of those problems can boil down to what we call machine learning problem or classification problem. So as an introduction or sort of starting point to doing the semantic structure for motion, we will take a look at that. But perhaps what's even more important here is that when we do these kind of research, we cannot just use one image or 10 images and try to do some tests on. We need to gather enormous amounts of images or other data. So very often we end up handling what's called big data. And we're not only doing vision in the group, we're doing other types of analysis of other types of data. And the problem with these kind of data sets is that there are several different types of problems. One is that they're so large, so it's a practical problem having them on hard disks and doing computations and what algorithms can we use and things like that. But another problem is that they can vary in type. They can be, we work on audio, we work on radio signals, on images. It could be text information or other types of data sources. And that can be problematic. Sometimes you need to do this extremely fast because you might get a new image every 30th of a second. So doing this in real time, fast algorithms can be a challenge. But perhaps one of the most difficult problems is in terms of that you might have a lot of missing data. So you assume that you have these measurements from all of these different samples, so patients, for instance, in medical image analysis. But then you have some missing values, or have some bad values from bad sensors or things like that. So always you have to keep in mind that you have outliers and missing data and small errors, but also large errors. And that's extremely challenging to work with. But also interesting and fun. So for instance, data, sort of problems that could involve lots of data is if you want to take an image and you want to search for that image among all the images on the internet, that's big data. We have research questions where you might have millions and millions of images and you want to do 3D models using all of them simultaneously. So that's challenging. We could have medical data from large populations. So even though each data set is small, because you have them from such a large population, it becomes like a large big data problem. Or it could be a small sample of the population, but you have such a large, you might have the whole genome and epigenome, and you might have terabytes of data from each patient, and then that becomes interesting, fun, and challenging. But perhaps the one that I'm most intrigued about right now is that there are so many interesting questions in terms of smart cities, and where you have sensors and you have different types of information that you can use to analyze what's happening, what's going on in sort of a complex scale in terms of transportation or energy efficiency and things like that. And that's something that we are working on and we are very much interested in. Okay, so but we'll start giving a few examples of things that we did. And in terms of saying Internet of Things or connected equipment, this is an old project that we did 15 years ago. It's a master thesis project, which then continued, financed by Electrolux. They wanted to make intelligent fridge, and we did an intelligent fridge. We did two prototypes. The first prototype was made in the math department, where we had 2 cameras and a very simple setup where we could analyze the content of 1 shelf in the fridge. And then we made another prototype where we had 4 cameras in the door, so when you open the door to the fridge, then you get the light on and you can see what's going on. But you have the cameras then looking at the content of the fridge. But we also had a camera mounted downwards towards the users, which could detect whether you're actually putting something in or taking something out or rearranging in the fridge. So that camera did the classification of those 3 actions. And then the cameras in the door made the analysis of what's going on in the fridge. So we did segmentation, that is cutting out the pixels that belong to a certain object. We did recognition of a number of categories of objects, but we also did 3D reconstruction of the content of the fridge. So you could get a 3D model which you could view from at home. And here we had the result viewed in Netscape browser, so you could see when you put something in, when you took something out, what did you put in, and so forth. And this was, as I said, in the year 2000. And then we had the IT crash, the IT bubble, so Electrolux didn't want to continue this. But maybe this is something we should do more again, I think. Here's another question. If you're given an image, search among all images on the internet, can I find what this comes from? This particular image, you run it through the algorithms, and you find out that it's the cover of a book, At the Mountains of Madness by H.P. Lovecraft. And this is something that one of our former PhD students did, who's now working at Google, and they use very clever algorithms for doing that type of image analysis. And here's another research question. Can you, from image mounted above, analyze what the flow of people, what's going on in the image, and calculate how many people enter and exit in the image? I will skip that. Okay. So just as an introduction into sort of the semantic structure of motion, we'll look at a very simple example. We'll assume that we have lots and lots of measurements of 2 categories, say apples and bananas. And we have measured 2 properties of those fruits, so maybe the length or the width or something. So on the x-axis you have the length, and on the y-axis you have the width. So each of these dots are the 2 measurements of one of these examples. But then we also have the labels. So we have some are labeled red because they are, say, apples, and some are labeled blue because they are bananas. So the machine learning problem is that if you're giving a training data, may given 200 examples of apples and bananas, and you measure their properties, somehow from these 200 samples, you want to figure out what's the decision boundary? Where should I make the boundary between apples and bananas? And here it's fairly clear that on the upper right-hand corner, it's the category red, and the lower left corner here, it's the category blue, and there should be some transition here, somewhere in between. And this is basically the image or the classification problem. You have some data, you have some training data, and then from that training data, you want to develop algorithms that can, for nuancing data, do the right classification. And that's very much connected to statistics and also to algorithms and machine learning. So there are several sort of simple algorithms. One is called the nearest neighbor, where you just take a new point, you check which one was closest. So if I take a new point, I want to figure out what should this be classified as. Then I check which one is closest. It's this one. If it's red, then this one should also be classified as red. So it's a simple algorithm, fairly efficient anyway. But there are more clever algorithms that can use, that can give better and better decision boundaries. And one of them, fairly nice algorithm, is called the Logistic Regression, where you actually try to estimate the probability of a certain sample being red or blue. And that logistic regression can be thought of as a very simple model of a neuron in a brain. So these kind of simple methods for doing classification has some sort of coarse counterpart in what's going on in the brain. And in deep learning, we try to take this a step forward and not only model a single neuron, but not model a deep complex of such neurons. And we will hear more about that in later talks. Okay. But usually we don't only have two measurements. Usually you have much more measurements. And in order to check whether our algorithms work, you need huge databases, preferably so that you also have the ground truth. So here's an example of such a database. If you want to do algorithms that do face recognition, you have to have lots of images of faces, and you have to have some ground truth on whether you're doing the right thing or not. So typically in these databases, you have pairs of matching faces. So you have Kevin Costner, Barack Obama, and lots of pairs where you have matching faces. And then you have a list of non-matching faces, and you can write algorithms that, given two data, try to figure out whether it's matching or non-matching. And then you can evaluate your system, and you can get sort of receiver operating characteristic curves, which you want to be as further up to the left corner as possible, because that's sort of the best result. And when we did this a couple of years ago, the best algorithm was the purple one over here. So maybe I can see that. So there's a purple curve that's about 80–90%. But then there are three curves that are much, much better, and those are the human performances. So we try these on humans in three different difficulty categories: easy, medium, hard. But even the hard category for humans did much better than the easy categories for all of the computers. But that was the state of the art a couple of years ago. But then came the deep learning algorithms, and now actually in some of these tests, the algorithms are much better than humans. But we also try to do other types of image analysis problems. So one type is this semantic structure of motion, where you want to, given an image, you want to find out automatically the segmentation, the pixels that belong to an object, but you also want to classify whether it's, say, a dog or a cow or a human or a table. So this is going towards understanding the content of the scene. So this is something we are working a lot with, and one of the professors in our group, Cristian Smichicescu, has been very successful in writing such algorithms. So he's been a winner of some of these challenges where you compete against other research groups in the world. And we're now trying to do that with a little bit of 3D information as well, with some both color and some depth information to do reconstruction of and understanding of what's in the image. But I'll skip the deep learning a little bit, and then we'll go into some examples of 3D reconstructions. And I think I'll actually go to the sound experiments first. So here's an example with sound, where I'm walking around in a room playing a song. And then there are a couple of microphones just placed randomly. So we have the sound source, which is moving in some unknown path, and we have the microphones that are in unknown positions. And the question we want to solve here is, given these kind of sound sources, can you just from the sound files, say 8 sound files, can you figure out where are the microphones and how has the sound source been moved? And it turns out that the differences in distance from the sound source location to the microphones. So if a microphone is further away, and then it gives sort of a time delay of the signal. And even if you don't know where the sound source is, you can do signal processing on the sound, two sound channels, and detect sort of tracks in how well they correlate. So even if they're very noisy, even if you have reverberations in the room, you can, using robust methods, detect these tracks. And from those tracks, you can do the geometry, the mathematics, to calculate both how the sound source path has been and the position of the microphones. And furthermore, you can calculate the position of the acoustic mirrors of the microphones in the ceilings and the walls and the floors. And from that, you can actually calculate the ceiling and the wall and the floor. And just to verify this, you can project that sound source path in the original video just to sort of visualize it and see whether you're doing the right thing or not. And we'll see here how it works. The green dots is where we think that the sound source is based on the audio, and you can sort of verify that it's doing more or less the right thing. So this is an example of a geometric problem, a structure from motion problem. This kind of geometry problems that we are talking about. What's interesting is that there are two objects here, two things. We have the sound source, which is unknown, and we have the microphones, which are unknown. But even though everything is unknown, you can actually solve for both of them. And once you've solved, say, for the microphones, you can use them as a sort of reference map so that when you get new sound events, you can localize them. So you can get sort of an indoor localization system with, say, a millimeter or centimeter precision, just by putting up some microphones and listening to what's happening. That means you can do speaker tracking, you can do beam forming to focus the sound on who's talking right now, or you can do indoor localization for other purposes. So this is an example of doing what we call structure from motion. What we usually do here is to do this from images. I mean, that's how we all got started on this. So the question for images is exactly the same. You take a number of images, but it's unknown where the images, how you moved when you took the images. So that's like doing the sound source path. You have some 3D structure, let's say the castle in Örebro in this example, which is an unknown 3D structure. And that's like the microphone positions. And you want to, just from the raw data, the bunch of JPEG images, you want to calculate both. You want to calculate both how the cameras moved and the 3D structure of the scene. And there are similarities here as well. To do this, you need to find and do correlations and find matchings between different images. So that's doing matching between different sound sources. And once we have the matched tracks, so we know which red interest point corresponds to another red interest point in another image, we can use that information and lots of mathematics and geometry to do 3D reconstruction of all of those image points, feature points in 3D, and the positions of the cameras. So that's like the microphones and the sound source path. Once we have the 3D reconstruction, we can use it for many purposes. We can use it for visualization, gaming, architecture, but we can also use it for localization. If I take a new image, I can calculate where I am relative to this sort of local map. So in an example, another project, we had a PhD student who did structure from motion from all street view images in Malmö. And then when you tried it on a new image, you could get roughly a decimeter, a couple of decimeters precision in localization, just based on these images. So what you see here are all the 3D interest points in Malmö. And most often, the images are taken from roads, so you sort of see the road network here. And we try to do the same thing with other types of sensors. Here's first example. One of the applications of these 3D models is actually to make 3D models that people want to view and use. And these are examples from Apple's maps, which are made by a research group at Cupertino, which is basically the C3 company in Linköping that they bought. But there are several researchers from our group that are working on algorithms for doing these kind of structure for motion from images. So again, they are flying over cities. They have lots and lots of images. From those images, you want to make these 3D reconstruction, 3D models of cities. But we want to go on and do that with other types of sensors. And there's an interesting radio technique, an ultra-wideband technique, so that you can measure the distance from your mobile telephone to sort of small ultra-wideband tags. Again, you get some, these are like the microphones, and the motion of your mobile phone is like the sound source. There's a game where you want to do both, find out both where the tags are and the sound source, so you get a map. But once you have a map, you can do indoor localization and find out where you are. And this is extremely interesting because other techniques like GPS, which work relatively good outdoors, they totally fail indoors. So you have to have some alternative techniques. And these are interesting, and also using the existing infrastructure like Bluetooth tags and Wi-Fi is interesting to try to do indoor localization well. But all of these connect. They have the same kind of basic mathematical, geometrical questions that you need to solve. So here we've done experiments where you can get sort of decimeter precision of the mobile phone relative to just some random tags that you put out in a room. So go back there. And so I want to sort of end, so we have a few minutes here, by trying to see what we should do in the future and what we are doing some initial experiments on. And that's trying to do both of them at the same time. So we're trying to use, say, small helicopters or drones or something, and you want them to be totally autonomous. And we want to use them so that you can, say, do the mapping of a building or a room autonomously. But that's tricky in the beginning, because in the beginning you don't know anything. You have no infrastructure, no positioning system in the beginning. So it might be that you first have to do some exploring to get some first rough draft of your map. And then based on that map, you can do further navigation and further 3D reconstruction of the map. But in the end, we want to do these kind of 3D reconstructions that we did from, say, images, but possibly from other types of data. But not only that, we want to segment those 3D models into different parts and do the semantic structure for motion from them. So we want from those different point clouds or triangulated meshes, we want to say that this is a cathedral, or this is a window or building, and so forth. But it would be interesting to combine all of these semantic understanding of images with these 3D models, so you can get something that uses both of these two words. And we think that the 3D structure for motion could help in doing a better semantic model of the images. If we know the 3D structure, it's easy to recognize that something is a chair, for instance, because of how it's set up. But we also think that the semantic understanding of images, if we know that this is a door in image 1, and later on we get a new image and we see it's a door, then we know that probably they should be corresponding. So the semantic understanding would probably help us in solving some of the difficult problems in 3D structure for motion. So what could that be used for? Well, we think that there's an increased use for indoor localization, but also finding out what's actually going on. If you want to do inventory of a store, of all your products, say a food store, these kind of systems could perhaps help you do that automatically. You could have sort of drones doing a mapping each evening or each night. Are all the food shelves, are they empty or filled, or are they positioned in the correct way? Or it could be that you want to do inventories of other things like the library or your stuff at home or other things like that. But I think that as you develop these kind of techniques, they are also enablers, so that when you develop the techniques, we cannot really foresee what kind of uses we can have for, say, mapping and localization. I think once you've got a good indoor localization system, say not only a 10-meter precision, but a meter precision or a decimeter precision, you can do other types of use cases for users, for finding things in your store, or for finding your stuff at home, or for finding your way. And I think that it's very interesting to see how these kind of things like map making and localization can be an enabler for IoT applications, using new sensors and solving new interesting problems. So that's me trying to keep the time. Again, I want to emphasize that the research that we want to do, or that we're doing, are these two types. We want to recognize what's in a scene: horses, dogs, windows, buildings, but also doing 3D models, not only based on images, but also based on other sources. So with that, I would like to thank you for listening, and I'm open for answering questions.
Thank you, Kalle. You're talking a bit about the usage of this. Do you find that pressuring? Do you find it difficult to always have a usage for research? Does that keep you in strains a bit?
No, that's exactly the fun part. Mm-hmm. It is the fun part, and I think many times we get sort of requests from, could be from other research groups or from local startups or even big companies that say, oh, we heard you're doing these things, couldn't we use this for this, or so forth. And many times when you start probing what's actually going to need, you realize, well, that's very interesting. We have these tools and they can be used, but we probably need to solve this as well. So it's the applications and the uses, they often fuel the sort of the basic research questions. Yeah. And then it's sort of a split vision. Sometimes you have to do the basic research questions and sort of be the nerdy mathematician, wondering about the proofs of a certain theorem. And sometimes you need to be the entrepreneur, understanding how this can be used in other. And I think, at least I enjoy playing these kind of games. Not doing the same time, not doing the same thing all the time.
Okay, I can understand that. And also sometimes I guess when you find something, you suddenly realize that this could be used for this that we never thought of.
Yes.
The serendipity.
Yeah, the serendipity factor.
That's very nice. So we're going to see if the auditorium has any questions for you. Åsa is here with the microphone, so please just raise your hand and see if you have any questions for Kalle.
There was someone.
Second row here, Åsa.
Hi. Are you focusing on image recognition for your research? And the last part you described about feature recognition and categorization and stuff.
Yes.
I'm thinking about there are new products coming up with the new depth sensors and the stereoscopic stuff, like Google's Project Tango.
Yes.
So is this going to help you, or do you have, in your research, or do you have to modify your algorithms, or?
No, it's a very good question. It's definitely going to help us, I think.
Yes.
And so again, we're a research group of roughly 20-25 people. And some of the PhD students and senior researchers are focusing very much on the recognition problem. So for instance, Cristian Smicisescu. And he's working not only on ordinary images, but also on these RGB depth images, where you have Kinect type sensors or other types of sensors where you get both image and depth. So it's definitely a relevant question. It's changing a little bit on how you are going to work, but new sensors give new possibilities to get a sort of better performance and so forth.
Yes,
so we are very much interested in that.
Right now, drones are mostly regular cameras, but they could use a lot of sensors, of course.
Definitely, and I think depending on what type of drones you have, I mean, you have everything from sort of the 20-gram drones to kilogram, or we have in research projects in WASP and maybe we will see that later. We will see drones which weigh 200 kilos. So the 200 kilo drones, they could have lots of interesting sensors, but the 20-gram drone might not even have a camera, or might have a 1 gram camera or something. So these are the practical limitations of different applications.
So would you say it's possible for you to suggest what type of sensor would help your research?
Yes, I think we can. But also, so it's both that if you want to solve a particular problem, we could suggest that this would be a good sensor. But sometimes it's also fun to play the game as a researcher. Okay, what if we only are allowed this type of sensor? What can we do with that? Sort of, if you put sort of constraints on what you're allowed to have. Sometimes that gives sort of interesting research questions as well. So you need to sort of do both.
Okay, thank you.
Any other one? Any other person has a question for Kalle? Ja, här också.
Hi, thank you for a very interesting talk. You didn't talk anything about complexity. I mean, do you work in real time?
Sometimes we work in real time.
Okay.
But for some questions, sort of, we just want to probe, is this possible or not possible? And then we very much work in offline, sort of, to sort of have some data sets, write code that evaluates on that data set and develop the algorithms. So again, I mean, it's a field where you sometimes in some projects need to get the algorithms working in real time, and sometimes we allow ourselves to just
So this identification problem with the church in Linköping, is that real time to identify?
The 3D reconstruction, you mean? We have projects where we do that in real time.
Okay. And what is the accuracy of the camera positions?
It depends on, I mean, basically it's a scale thing. If you have a large scale object and you're far away from it, then you get sort of the relative position. I mean, so it's poorer precision. And if you have a very small scale object and moving very closely to that one, you will get a fine position. So typically in the city, we had like a decimeter precision of the camera. If you're moving inside a small room and you have a lot of structure, you might get centimeter or millimeter precision. And it depends on the sort of the resolution of the sensor as well. But that's sort of the ballpark of the.
Okay,
position.
thank you.
Yeah.
Thank you. Kalle, you will be in the meet and greet area also.
Yes.
For further questions. So we give a round of applause for Kalle and your presentation.
Tack så mycket. Ja, trevligt.